All right, in this one we're just going to look at some applications involving exponential functions where we can come up with an equation and then work our way through and solve them. For exponential growth and decay, what they do is they give you an equation where they talk about n equals n null times that quantity, 1 plus r, all raised to the t power. Now, you truly can get by with our general form like I've been using a times b to the x. Because if you think about when we looked at those things, a again was my start point. If you look at n sub null, it's talking about your initial point. So that's how much we start with. Okay. Our final amount is our y. Okay, so in all those situations, what we were doing is we could plug in an x value, and then an y value got kicked out. So that's why I ended up with. So we can look at that as my final amount. Okay, if you look at x, that's how many times we're going to multiply by that base b. Well, see, and that's what t is here as well. Number of times periods, or how many times we're going to go through and raise to that power. So the piece that can sometimes give us a little issue then would be the 1 plus r, and it actually could be minus. Okay, when we have decay, it's going to get smaller, so we use the minus. When we have growth, we're actually going to use the plus. This is a place where a lot of people make mistakes. That's going to be your rate of change, your b value. So if you have the formula given to you, it's probably easiest just to go in and plug those numbers in and run with it. But we could get to a point, hopefully, where you can think about, hey, what did I start with? How is it changing? Okay, and one of the things like I talk about a number of times with the idea of that rate of change is that if something is increasing by 7%, okay, two mistakes that happen when we increase by 7%. One, we don't correctly list it as a decimal, okay. 7%, again, what you can look at with 7% is that it's 7 per 100. I don't know what just happened there. So 7%, we can look at it as 7 per 100. And we can always type that into my calculator and make sure that I get that 7%, okay, in the correct decimal place. The other thing is if it's increasing, then all of a sudden we throw in this formula, 0.07, and I go through and calculate, that's decay. That number is less than 1. Okay, so the number gets smaller, and people are like, what did I do wrong? Well, because it's getting bigger, you need to include the 1, which brings the original amount with it, and then the 0.07, that's adding on the interest or whatever we're adding on here to your original amount. Second one is when we deal with depreciation, if something's getting smaller. Okay, say if something's depreciating by a rate of 10% every year, if I put that 10% in there, that's a big jump right away. So if I start with something that's worth $100, if it depreciates by 10%, it's only going to be worth $90 next year. But if I use that 10%, okay, now all of a sudden it's only worth $10. So you got to be careful with what you enter into that. Okay, so here's the situation. Your goal is to buy a car in 5 years. You figure it's going to cost you about $14,000 to buy a decent used car. Okay, and then how much do we need to put away now if the interest rate that I can get is 4.5%? Okay, so like I said, we can go in and use the formula since it's given to us, and sometimes that's going to be easier. But at the same time, I'm going to show you how it also works to be y equals a times b to the x. Okay, so as I go through, I'm going to look at each of my numbers. 14,000, that's what I need to end up with. Okay, so at the end, I need 14,000. Well, again, like I said, that's where we want to end up with my y value. Okay. 5 years, that's my time. Okay, well, in this formula, it's how many times I'm going to multiply by my rate of change. Okay. Interest rates, 4.5%. 4.5 over 100, 0.045. Make sure you get the correct decimal. Okay, again, that's what kills people a lot of times. So now what I have is 1 plus 0.045. Okay, well, and what I think about with my rate of change as well, if it's increasing by 4.5%, when I bring with the original amount I put in, there's my 1, and I'm going to add in that 4.5%. Okay. And then I still have my initial that I need to find. Okay. Now, to calculate this, one of the things to deal with is try not to round off until your final answer. Okay, because if you round off and then you do more calculations, your answer gets farther away from what it should be. So what I look at a lot of times is that, hey, I'm just going to go in here and I'm going to divide by this. The 1 plus the 0.045 raised to the fifth on both sides. So this will multiply out to 1. And so now the initial amount that I need to invest. Okay. If we go in here, if I type it in exactly as I see it, 14,000 divided by. Well, now I got to set a parentheses, 1 plus 0.045, okay, all raised to the fifth power. And there's my solution. Now, think about your situations here too. You're dealing with money, so we're going to round it off to 2 decimals. So I'm going to have $11,234.31. Okay. Now, the other way we could look at that in terms of our typing it into the calculator. One, what I could look at, and I'm going to go back to this level right here. Okay, I can determine what the 1 plus 0.045 is, or add those two together, and then raise that to the fifth power, and get a value for that chunk. And now recognize that I'm going to divide both sides by that. And here's the thing with your calculator. If I take 14,000 divided by, I want to bring back that last answer. I want to bring back that 1.246. And if you use your second negative, that brings back that last answer. Okay, I get to the same point. All right, another special type of exponential function we'll see a lot of times is when we talk about compound interest. You go to the bank, put your money in there, IRAs, put some money in there, certain interest rates. Compounded means they're going to add interest to it at different times during the year. Okay, but it's, again, pretty much the same formula. Y equals A plus B, or times B to the X. Okay. All right, now we're going to talk about how those things come about. Okay, A is pretty easy to see. Okay, your start point, because that's your principal. That's what it's called. Principal is what I put into the bank to start with. Okay, A, that's what I end up with. That's your final amount. Again, this is a capital A in this formula. When I mentioned A earlier, I'm talking about little a, and the Y equals A plus BX. Okay. The N and T. Okay, when we get into that, N talks about the number of times that we add interest in a year. Okay, so that's going to change depending on our situation. Okay, if we talk about it being compounded yearly, that means we're going to add interest once a year. So if I went in and started an account today, next year on this date, they would add the interest to it. Okay, if they talk about semi-annually, that means they'll do it twice a year, or in 6 months from now, they're going to add interest on it. Then 6 months after that, they'll add interest on it, so on and so forth. They might talk about quarterly, which would be 4 times a year, or monthly, which is 12 times a year. They might do daily, 365. Again, disregard leap years. Okay, so your N is how many times we're going to compound that interest. T is your number of years. So if you think of Y equals A times B to the X tells you how many times we're going to multiply by my base. Well, if I'm going to put my money in the account for 5 years, quarterly, okay, that means 4 times each year. That means 20 times they're going to add interest to it. Okay, so there's where the tie-in is with the X. Okay. Now, the piece inside here, my rate of change, my base, is going to be 1 plus R to the N. Okay. 1, because that's the original amount. They're going to add the interest rate, okay, divided by how many times we compounded in a year. Interest, or the idea I use a lot of time here is a credit card. Okay, if you get a credit card, there's going to be an annual percentage rate that you're going to pay. And let's just say it's 18%. That does not mean that every month when you get your bill, they've added 18% on to your bill. Okay, what they do is they take that 18% and divide it over a full year. Okay, so at 18% divided over 12, each month they're going to add 1.5% to your bill. Okay, So again, that's what's being added. That's a little more difficult one to think about if I'm trying to use the y equals a plus b to the x, but you can kind of, if you remember that idea that they break it down, might make it a little easier. Okay, so Lindsay puts $475,000 into a Swiss bank account, 3.5% interest rate, wants to put the money in there for 25 years. If it's paid out quarterly, so 4 times a year, how much will be in the account when she takes it out in 25? Okay. Truly would suggest you just go ahead and use this formula. On the test, you'll be given the formula. Okay, so A equals P1 plus R over N all to the NT. Okay. So 475. That's your initial amount that she's putting into the account. Okay. 3.5% interest. Okay, so again, 3.5 per 100, 0.035. That's your interest rate. Okay. We want to put it in there for 25 years. Okay. And then finally, because it's quarterly, here's where we have it. So not adding 3.5% each time, they're doing 3.5% divided by 4, okay, whatever that comes out to be, and then we'll look at our final amount. Now, the nice thing, again, with my calculator, I'm able to simply type this in as I see it, okay? So, 475,000, okay? Now I'm going to go with the parenthesis, 1 plus 0.035 divided by 4, okay, raised to, now because I'm doing 4 times 25, if I'm doing a product in there, what I want to do is put that piece in parentheses. Yeah, most of you should be able to just say, hey, that's 100, but I'm just showing you for different situations. And so when she's done here, she's going to have 1,135,000. Okay, $137, and again, because we're dealing with money, round it 2 decimals, 27 cents. All right. So for these applications, you'll be given a formula, plug the numbers in, and go from there. That shouldn't be too bad. All right, good luck.